You ever look at some of the massive machines that run our world? Jet engines, giant power plants, and just wonder what keeps them from tearing themselves apart? Well, it's not magic. It's a marvel of precision engineering, and it's usually hidden deep inside. Today, we're going to pull back the curtain on one of these unsung heroes.
Just look at this number, 50,000 revolutions per minute. That's how fast some industrial compressors can spin their central shaft. We're talking over 800 times every single second. So how in the world does a massive steel shaft spin at these absolutely insane speeds without generating enough friction and heat to literally weld itself solid?
And get this, what could a machine like that possibly have in common with a simple skateboard? Well, the answer is the same for both. It's a small, brilliant little component that managed to conquer the single greatest enemy of motion, friction. And by the end of this, you're going to see exactly how it pulls it off.
Okay, let's dive right in. And we're going to start with the big machine itself, the centrifugal compressor.
So what does this beast of a machine actually do? Well, its main job is to take a gas, like air or natural gas, and shoot it out the other end at a much, much higher pressure. And it does this using the power of centrifugal force. The same force that tries to fling you off a merry-go-round when it's spinning really fast.
The whole process is actually pretty straightforward when you break it down. First, gas gets sucked right into the center of a spinning wheel, which is called an impeller. Next, that impeller spins incredibly fast, flinging the gas outwards and getting it moving at a ridiculous velocity. And finally, as that super fast gas leaves the impeller, it's forced into a space where it has to slow down, and all that speed gets converted into immense pressure. It's an elegant idea, but it creates one heck of a challenge.
And that brings us right to the core engineering problem here. How do you deal with the insane forces you get from all that spinning?
Just try to picture that massive, heavy shaft spinning thousands of times a minute. If it were just grinding and sliding against its housing, the friction would be catastrophic. The heat would build up almost instantly, the metal would warp and seize up, and the entire multi-million-dollar machine would destroy itself in seconds.
This is the perfect way to think about it. Trying to spin that shaft directly is like trying to push a heavy book across a table. That's sliding friction. It's tough, and it creates heat. But what if you stick a few pencils under the book? Suddenly it moves with almost no effort. That's rolling friction. And that simple idea is the secret to making these incredible machines possible.
So, how exactly do you put pencils inside a high-speed compressor? Well, you use one of the most important yet overlooked inventions in mechanical history, the bearing.
This little guy right here is our hero. A rolling bearing is basically a set of super precise, perfectly smooth balls or rollers that are sandwiched between two rings, called races. The inner ring gets attached to that spinning shaft, the outer ring is fixed to the machine's housing, and those rolling elements in the middle, they let the two parts move almost frictionlessly against each other.
Now, bearings are specialists. They're designed for different kinds of forces. Think of a radial load as the weight of the shaft just pushing down on it, because of gravity. But that compressor is also generating this immense force that's trying to shove the shaft forward, right out the front of the machine. That's called an axial load, or thrust, and it needs a completely different type of bearing, a thrust bearing, to handle it.
And the benefits of this design are just incredible. They have almost zero friction right from the get-go. They can handle those mind-boggling speeds we were talking about. And since they're standardized, you can just pop an old one out and put a new one in. They're built to last, which makes them the perfect solution for this absolutely brutal environment.
But here's the thing, not all bearings are created equal. Engineers need a way to specify the exact right one for the job. And to do that, they use a special code.
If you ever look at a bearing, you'll see a code like this, stamped right on the side, 6203ZZ. Now that is not just some random model number. It is a dense little code that tells an engineer everything they need to know about that bearing's design, its size, its capabilities. It's a language of pure precision.
Let's just break this one down real quick. Every part tells a story. That first digit, the 6, tells us it's a deep groove ball bearing. That's the most common kind. The O3 actually tells us the diameter of the hole in the middle, which for this one is 17 millimeters. And that ZZ at the end, that just means it has metal shields on both sides to keep dirt and grime out. See? Every single bearing has its own story, told right there in its number.
Now, a bearing, as amazing as it is, doesn't work in a vacuum. It's a critical part of a much larger system where every single component has to work perfectly for the whole machine to survive.
This might sound a little crazy, but the fate of a massive, multi-ton machine can literally come down to a gap so small you can't even see it.
That tiny gap is called internal clearance. It's the little bit of wiggle room between the balls and the rings. If that clearance is too tight, the bearing is going to overheat and fail. If it's too loose, you're going to get a ton of vibration, noise, and, you guessed it, it's going to fail. Getting that clearance perfect is absolutely critical.
But even if everything inside is perfect, there are outside threats. And in the world of compressors, there is no word more terrifying than this one: surge.
Okay, so imagine the compressor is trying to push air into a pipe that's already completely full. If it can't overcome that pressure downstream, the flow can just stop. And then it violently reverses, shotgun blasting backwards through the compressor. This insane cycle of stop, reverse, forward can happen dozens of times a second.
And the results are immediate and violent. You get these massive pressure spikes, loud banging noises that sound like the machine is tearing itself apart, and a huge, sudden jump in temperature. Each one of those flow reversals puts an incredible shock load on the entire rotating assembly, especially those critical thrust bearings. A really bad surge event can literally destroy a compressor.
And finally, none of this works without one last thing: lubrication. A constant flow of clean oil is what creates the microscopic film that prevents metal from ever touching metal. At the same time, it's also carrying away all that immense heat the machine generates. The oil really is the lifeblood of the bearing. So when you step back and look at the whole picture, it's pretty amazing. You have these colossal machines spinning with almost unimaginable power, and their survival depends on this small, humble component that relies on microscopic tolerances, a secret code, and a constant battle against friction and heat.
From your skateboard all the way to a jet engine, the rolling bearing is one of these hidden marvels. It kind of makes you wonder what other incredible feats of invisible engineering are all around us, just hiding in plain sight.